All right, everybody. Here's an example right off our assignment about implicit differentiation. Okay, so I'm given this equation, and this equation gives us what's called an implicit function. It gives us y as a function of x implicitly, and I want to find the derivative dy over dx first. We can also call that y prime if we want to. And then once I find that, one of the things that the derivative can tell us is the slope of the curve. It could also tell us the rate of change between y and x, but in this case, we find the derivative and then use that to find the slope of the curve at this point on the curve. Okay, so let's do that. So I'll divide this into parts. So part one, as I'm doing it, will be part A of the question on my math lab. And it's to calculate y prime, or if you want, dy over dx. What's the difference there? They're different symbols for the same thing. Okay. All right, so how would we do that? I would do that in two steps, all right? So I have this equation that gives me an implicit function, and I want the derivative, and I'll find the derivative in two steps. Here are those two steps. I take the derivative with respect to x of everything on both sides, every term, both sides of that equation right here, with whatever rule is applicable. Because you know, finding a derivative, well, that requires you use the correct rule, and there are different rules for different situations. Okay, so I take the derivative with respect to x of everything here with whatever the rule would be. Okay, so for the first term, 3x times y to the 1/3 power, that's a product. It's the product of two functions. You know, 3x is a function, and then it turns out y is a function too. It's just that we don't have it solved explicitly as a function of x, but it's still a function. So I find the derivative of 3x times y to the 1/3 power with the product rule, because that's the rule that's applicable. So here's the derivative from there. The derivative of 3x is 3 times y to the 1/3 power plus the derivative of y to the 1/3 power is 1/3 y to the -2/3 power, then times y prime. So in this method of implicit differentiation, we find the derivative of everything with the rule that's appropriate, but we always multiply all y derivatives immediately by y prime. Okay, so that's why I say here, the derivative of y to the 1/3 power is, well, according to the rule, we bring that power down, then we subtract 1 from that power, so we get 1/3 y to the -2/3, but I multiply that immediately by y prime. And then multiply that by 3x, and that concludes the product rule. So this entire thing right here is the derivative of 3x times y to the 1/3 power by way of the product rule. And then I would carry down the plus, because the rules of derivatives say we can do that. And then the derivative of y would just be 1. But remember, I said we'd multiply all y derivatives immediately by y prime. So this is a 1 y prime. We carry the equals down, and then the derivative of 44, well, 44 is a constant, and the derivative of a constant is 0. Okay, so I get this. Now, whenever I get something by the rules of calculus, I'll typically also simplify it before I do anything else with it. And I notice here that I get a 3 and a 3 that will cancel. I get 3 times 1/3. So those 3's are gone. And then among what's left, I get x times y prime, and I've got this y to the -2/3 power. And that's what I can do to simplify it. There's not much else meaningful. Okay, so that's my first step, is apply the derivative all the way through, all terms on both sides with the rules as they apply. All derivatives of y get multiplied immediately by y prime. Okay, step 2. Well, what do you think step 2 is? We're trying to find y prime, or dy over dx, whatever your choice of notation is. Say if you wanted that, I mean, it's right here and it's right here. It makes sense that you solve that result from step 1 for y prime. You try to get the y prime by itself. You try to rearrange this equation so that it says y prime equals, and that stuff you get on the other side is your answer. Okay, so I'll do this. If I was going to use algebra, that's all step 2 is. algebra. If I was going to use algebra to solve for y prime, I would move this term to the other side because it doesn't have a y prime in it. Then I would factor out the y prime and make it look like so. And then when I'm here, I'm just one step away from the answer. If I divide both sides by this, then I've isolated the y prime and I've got an answer for you. It says y prime equals negative 3y to the 1/3 power over x times y to the negative 2/3 power plus 1. And there's your derivative. That's your answer for part A, part 1 in my case, right here. Okay, your derivative dy over dx. Okay, they called it dy over dx. Doesn't matter. I could call it y prime or dy over dx. It's a little simpler, I think, through this procedure to just write y prime. So that's what I did, for now at least. Okay, I do think it's a little strange that this answer on my math lab isn't entirely simplified. We could factor out that 3 and cancel with that 9 and get the answer I have right there. So that's a little strange, but whatever. I can't argue with what they have there. It's just what it was when I copied it from the assignment. I would expect maybe to have to put this in because it's simplified. All right, so that's the first part. What's the second part? So it says, what's the slope of this curve at that point 6 and 8? Well, another way to phrase that question is to say this. Y prime equals what if x is 6 and y is 8? You could think of it like that if you wanted to. So I take my formula for y prime, which you see there, negative 3y to the 1/3 power, x, y to the negative 2/3 power plus 1. And I put 6 for x and 8 for y, which would look like that. Okay? I did this in my head. I don't think it's a bad thing to be able to do some math in your head. Cube root of 8 is 2 times 3, that's negative 6. This is 1 over 8 to the 2/3 power. So that's going to be 1 over 4 times 6, and so on. And I work this down to negative 12 over 5. Okay, and that is my answer. Like right there, it says the slope at the point 6 and 8 is negative 12 over 5. Now, I want to encourage you to think about this number a little bit. You can just go through and do the math, get your answer, and move on. But I'll tell you this, like about me, I really like classes like chemistry and physics because in those classes, I can do a bunch of math on paper, but then I can also go into the lab and do an experiment and measure a bunch of stuff and see that it agrees with my math, if I do it all correctly. I know there's experimental error, and of course you can make mistakes when you do math too, but if you do it right, what you do on paper should agree with what you see in the laboratory, and I really like that. I know that's not the way everybody is, but I really like that. I like to build things, I like to do experiments and so on. So here's what I would like to do for you, and I'd like to encourage you to think about it like this also. Apparently, here's what this means. If I could look at this curve right here, 3x, y 1/3 power plus y equals 44, and if I could locate the point on it where x is 6 and y is 8, then I should see that the rise is negative 12 and the run is 5 near that point, that's what it should look like. It should look like a line with a rise over a run like so. So here's what I did, because I told you I like experiments. I like to build things and so on. So I'm going to do as much as I can something like that right here. So what I did is I went to Desmos, and on Desmos I can put in a function or an equation where it's an implicit function and get it to graph it. And I see, a graph that's fairly complicated. But if I'm going to run an experiment to verify this, I'm going to have to look at that point 6 and 8. X is 6 and y is equal to 8. So what I did is I can zoom in and I can find that point. And when I'm zoomed out, I see a curve. I don't see a line. I don't see something straight. I don't see something that has a rise over run. But if I keep zooming in, I'm going to try to find that point 6 and 8. Look how the curve gets straighter and straighter and straighter the more I zoomed in. So what on the outward perspective was a curve starts to look like a line if you focus in more and more on any particular point. All right. So, okay, now here's the next thing. It should be, if what I did on paper is right, that this line right here, which is the close-up perspective of that curve at the point 6 for x, 8 for y, that point right there, it should be that if from point to point, if I go down 12, I have to go over 5. That's what it would mean for this to have a slope of negative 12 over 5. So here's what I did. I took a screenshot of that close-up view of the curve. Okay, there's 6 and 8. There's the point I was given in this question. And for convenience, I said, I'll look at this one and I'll go from there. So at this point, if I go down 12, counting the boxes, 1, 2, 3, 4. If I go down 12, it'll get to here. And sure enough, I have to go right 5, 1, 2, 3, 4, 5 to land back on the curve. This line right here, the close-up perspective of that curve at the point 6 and 8, sure enough, you have to rise negative 12 for a run of 5. Okay? And that's the experiment that proves or is consistent with my work on paper. All right. So I hope that gives you something to think about, and I hope it helps you understand this sort of thing a little bit better. And more than anything, I have to say, like, just because it appeals with how I like to think about things, I hope you liked seeing this experiment with the graph to support what we did on paper.